All right. Good evening, everyone. So today we are starting the second module, which, as I mentioned in the messages last night, is perhaps the most important module in this course, in the sense that all of the other modules will rely on connectivity, or they will make use of connectivity. Okay. So the module we are starting is about connectivity of graphs. Okay, and yeah, so I'll just mention briefly the importance. So as you have noticed already in some assignment problems and some discussions during our lectures, for many topics and problems in graph theory.
I think it will be module 2.
Oh, you're right, sorry, thanks, module 2. Thank you. For many topics and problems in graph theory, you can restrict yourself to connected graphs, right? So what does that mean? It means that if you solve your problem for connected graphs, you often end up solving the problem for all graphs in the world, right? You may restrict attention to connected graphs. So connected graphs is very simple, right? A graph is connected if there is a walk or a path, whichever you like, between any two vertices, right? However, in many areas of graph theory, as we will see as we keep moving on, you can actually restrict yourself to well-connected graphs. So in the same spirit, often you may restrict attention to well-connected graphs. What do I mean by well-connected? Well, it depends on the context, but we will need some terminology to make this rigorous, right? So this concept needs to be made rigorous. Okay, so what happens in many areas of graph theory, one area is planarity, which is the module 3 that we will be studying after this one. So if you want to understand planar graphs or non-planar graphs, whatever that means, in case you don't know the definition, that's fine. What you can do is, rather than looking at all graphs, you can consider graphs that are well connected. Okay, and if you solve your problem for well connected graphs, then you solve it for all graphs in the world. Okay, so the same phenomenon. And in order to make this rigorous, we will be looking at two types of connectivity: vertex connectivity and edge connectivity. These are the most standard notions of graph connectivity, and those are the ones we'll be studying. Okay, so we'll talk about these things later, but I just want to give you an overview of where we are heading. Okay.
Sir, I have a question.
Yeah.
So what is the definition of well-connected graphs?
Right, we don't know the definition. I'm just telling you that it needs to be made rigorous. Depends on the particular topic, right? Because I'm making a sort of broad statement here that in certain areas of graph theory, you don't need to look at all connected graphs. You just need to look at well-connected graphs, and the definition of well-connected depends on the area you're studying, right? And two notions that we will use to make this rigorous are vertex connectivity and edge connectivity. Right? So I'm deliberately being vague here because I'm not talking about a specific area at this point.
Okay.
Is that okay?
So basically,
Yeah.
sir, the definition of well-connected graphs will vary from context to context.
Exactly. In fact, we will not even use the term well-connected graphs. This is just to give you an idea of why this module is so important. Exactly. Right. So the well-connected graphs will depend on the context.
Context. So
Yeah.
in general scenario, we call it well-connected graphs.
Yeah. I'm just using a terminology to convey the big picture here.
Okay.
I'm not making a formal definition or anything.
Okay. Okay, sir.
Okay. Good. So let us start with a very simple concept. Today we will not talk about vertex connectivity and edge connectivity in general. We will talk about special cases of them. So I want to start by talking about cut edges that you have already seen on assignment 0. Okay. So let's look at the following graph. So this graph, well, it's clearly a connected graph. You can see that, right? But it doesn't have very good connectivity in some sense. In particular, there is this one edge. If you remove that, then the graph disconnects. Okay? So that kind of an edge, we are going to call it a cut edge. Okay, so you remove the edge and the graph disconnects if the original graph is connected. To make it more general, we will say that the number of connected components increases when you remove the edge. Okay, so an edge E of a graph G is a cut edge if the number of connected components in G minus E is strictly greater than the number of components in G itself. So notation, in case I haven't defined this before, this is the number of components of the graph G. Okay? So I have a question. How big can this quantity be?
CFG plus 1.
Exactly. If it is greater, then I think on the assignment you have already shown, assignment 0, that it will go up by exactly 1. Okay? So, observation, this is assignment 0. E is a cut edge of a graph G if and only if the number of components is exactly 1 more than the number of components in the original graph. Okay? I hope everybody can see this and therefore prove this. Any questions or concerns? Yeah? Okay, good. Okay, so a common term in graph theory for cut edges is called is bridges, but we will not use that because we will use that for something else in this course. So please don't use this term for cut edges. Okay? Good. All right. So, well, so basically a cut edge tells you that you can remove just one edge. The presence of a cut edge means that you can remove just one edge and the number of connected components will increase, right? So in some sense, the graph is not very well connected, right? Because of the presence of a cut edge. And that actually turns out to be the weakest notion of edge connectivity that we will be discussing 2 lectures later. But right now, let's just focus on cut edges. Okay, so well, you can ask one question immediately. Is there an alternative characterization of cut edges? Right, so we are looking for some result that says that an edge is a cut edge if and only if something else is true.
Sir, I think there exists two vertices UV such that every UV path in G passes through that edge, contains that particular edge small e.
It's not part of a cycle.
Okay, okay. So there might be multiple ways to phrase this. I will go with the second one, and perhaps you can also get the first one that Aranya is referring to. So an edge is a cut edge, sorry, is a cut edge. I forgot to write that. If and only if the edge does not participate in any cycle. Okay. So this is proposition 3.2, and it was already on your assignment 0. So it's do it yourself, and it was already part of assignment 0. Okay, so that's a very easy statement to prove using elementary graph theory. Okay. And when I say does not participate in, just to be clear, I mean it does not belong to any cycle. Good. So I want to rephrase this in a slightly different language. And I want to do that because I want to tell you about a beautiful conjecture in graph theory that's open for since the 1970s. So almost 50 years by now. Right? So let's recall the following definition. A one cover of a graph G is a family script F of subgraphs such that if you take the union of all the edge sets of these subgraphs, you will cover all the edges of the graph. This is the cover property. Okay. And the second property, why do we call it a one cover? Because we want each edge to appear in exactly one member in script F. Each edge appears in exactly one member in script F. Okay? And in particular, we talked about cycle 1 covers, which just means that all the subgraphs in script F are cycles of the graph. Right? So just to give you an example, I don't know, something like this maybe. So here you have a red cycle, a blue cycle, and a green cycle, right? And that is a cycle 1 cover of the given graph. Okay? So we know what a 1 cover is. So you can imagine what a k cover is, right? Each edge appears in exactly k members in the family script F. So this can be generalized to k cover, and well, you know, I can also generalize it to at most k cover, where each edge participates in exactly k or at most k members, right? Fine. So just to give you a quick example, if you take this graph and you consider the cycles that I'm drawing now, take this to be the red cycle, take this to be the blue cycle, take this to be the green cycle, and let's use one more color. Let's see, maybe I will use orange or purple or something, right? So that is an at most 2 cover of the given graph. This is an at most 2 cycle cover. Oh, sorry, I think we call it a cycle at most 2 cover. Okay? Good. Any questions regarding the definitions?
Sir, I have a question. So it is
Yeah.
not a cycle to cover.
What I have drawn here is not a cycle to cover. You can get a cycle to cover very easily from here, but I have given you an example of a cycle at most to cover.
Cycle at most
Every
to
edge is
cover.
used at most 2 cycles. Do you agree?
Yeah.
Okay.
But sir, does this graph has a cycle to cover?
Find one.
Yeah, if you add the rectangle, I think it should.
Yeah, that's right. But we are going to see a conjecture related to the question you just asked. Does this graph have one? Well, turns out lots of graphs have one, we just don't know how to prove it. Okay? All right. So, let's see. So let me ask let me begin with a very easy question. So if I don't say K, then I just mean, so you can also think about a cover. If I remove the 1, then I can also generalize it to cover. And cover just means the first property. There is no K, so we don't care about the second property. Okay? So let me ask you the following question. Which graphs admit a cycle cover? I just want to cover all the edges using cycles. How many times I cover them is not a concern. Can anybody tell me what is the answer to this question?
A graph which has no cut edge at all.
No cut edges, exactly. Right? The answer is graphs without cut edges. Right? Because if an edge is not a cut edge, then by the proposition we just discussed, there is some cycle containing that edge. You just throw it into your cycle cover. Right? So cycle cover just means only property 1 listed above. Does everybody agree? If your graph has no cut edges, then there is a cycle cover. You might use one edge 100 times, there is no problem. Okay? Good. What about the next question? Which are the graphs that admit a cycle 1 cover? So now I am putting a very big restriction.
Sir, I have a question. So can you just
Yes.
explain once again why the graphs without cut edges are exactly those graphs which admit cycle covers?
Right. Well, what is a cycle cover? It is just a collection of cycles so that every edge is used in at least one cycle.
Yes.
Do you agree? Now look at this
Yes,
proposition.
Yeah, is a cut edge if and only doesn't participate in any cycle. Okay.
Right? So for every edge, you can find some cycle containing that edge. Throw it into your cycle cover.
Okay, okay. And the cycles need not to be edge disjoint.
Exactly, we have removed the edge disjoint property.
Okay, okay, okay. Actually, I just confused with the edge disjoint. That's why I was
Okay.
stuck.
So the edge disjoint is taken care of in property 2 when k is equal to 1. Right? But now I have removed the edge disjoint and I have made it a second property so that I can generalize it.
Actually, in the definition of one cover, there is edge disjointness, but in the definition of simply covers, a cycle cover, there is no edge
Exactly.
disjointness.
In the definition of one cover, you have this property number 2, which is the same as saying edge disjoint. Each edge appears in exactly one member. Okay?
Okay, okay.
So I have phrased it differently from how I phrased it before. Okay? Good. Anybody else? Any questions or concerns? Is everybody convinced that if there are no cut edges, then you have a cycle cover?
Okay, so sir, if a graph has a cut edge, then that edge cannot participate in any cycle. So there is no
Exactly.
cycle. There is cycle
Exactly.
cover.
Exactly. So it is actually if and only if, right? So this is a complete answer.
Means basically a graph admits a cycle cover. A graph admits a cycle cover if and only if it has no cut edge.
Exactly. Okay? Good. So now let's move on to the next question, which we have already discussed earlier when we defined cycle 1 covers 2 lectures or 3 lectures ago. Which graphs admit a cycle 1 cover?
It will be even graphs.
Even graphs, right? This is exactly Veblen's theorem. Okay, good. So if you ask for one covers, if you ask for cycle 1 covers, turns out that the answer is a very restricted class of graphs. You want every vertex to have even degree. So let's try to relax the condition slightly. Instead of a 1 cover, let's ask for a 2 cover. Okay? So maybe the answer is not just the even graphs, but maybe there are other graphs which admit cycle 2 covers. So turns out we don't know. We don't know the answer. We have a conjecture.
Sir, I have a question. So if a
Yeah, go
graph
ahead.
admits cycle 1 cover, can we say that it also admits cycle 2 cover?
That is correct. If a graph admits a cycle 1 cover, then you just consider all the edges, all the cycles, you just duplicate them because the family does not have to be, it does not have to contain distinct cycles. So if your red, blue and green cycles are a cycle 1 cover, you just repeat them twice. Red cycle 2 times, blue cycle 2 times and green cycle 2 times. Okay?
So basically, any even graph admits cycle 2 cover, but we
Yes.
cannot say the converse.
That's right. That's right. And it turns out that there is a conjecture which says that every graph in the world without cut edges, because of course you can't have cut edges, admits a cycle 2 cover. And this conjecture is due to two people independently, Szekeres in 1973 and Seymour in 1979. They both conjectured this independently. Right? And more popularly, it is called the cycle double cover conjecture. I'm calling it a cycle 2 cover just to be consistent with our terminology, but it's generally called the cycle double cover conjecture. Okay? So no one has any clue how to prove this. Is the conjecture clear? I should say here that when you talk about these definitions, repeating the same cycle is allowed. Repeating the same cycle or the same member in script F
So
is
that's why
allowed.
we in the definition we say family, not a set, because
Right.
in a set all elements are distinct. In a family, it need not be.
Ah, okay, good, good. That's a good distinction. I generally use set and family interchangeably, but that is a good reason to use family. Thanks. Okay, and you might ask, why are we asking for a 2 cover and why not an at most 2 cover? So it turns out that is an easy exercise. So I'm going to leave this to you for as a do it yourself as well because it's actually quite easy. A graph G has, or maybe I'll say admits a cycle at most 2 cover if and only if it admits a cycle 2 cover. So one direction is trivial. A cycle 2 cover is a cycle at most 2 cover, right? So this direction is trivial and the other direction is easy using the previous module's knowledge. Okay? So finally, I just want to say that if you want to prove the cycle double cover conjecture, it is quite clear that you don't need to consider all graphs, right? You can look at just connected graphs. If you prove it for connected graphs, then you prove it for all graphs. So I don't think I'll write that down. That's quite clear. Are there any questions or concerns regarding this conjecture? Right, so my purpose of telling you about this conjecture is to just tell you that, it's not like graph theory has a lot of problems which are easy to explain, but as of today, we have no way how to answer these questions. Right? And the cycle double cover conjecture is perhaps the easiest to describe conjecture that is so difficult to prove. A lot of people have tried proving it and nobody has succeeded.
I don't see why you would repeat graphs in the family H. Isn't it true that if there's a repetition and you just remove one, then that is also a K cover?
Well, if if you repeat and you are using each edge twice, by removing a cycle, some edges will now be used once. Right? But if you are considering specifically the case of cycle 2 covers, then this proposition is telling you that at most 2 cover or 2 cover, they are interchangeable. So if one is true, the other is true. Right? But in general, that's not the case. Does that make sense?
Oh, by K cover, you mean there must be an edge which occurs K times.
Every edge occurs exactly K times. Right? Let's go back to the definition. Every edge.
Oh, I thought it is at least.
Okay.
Or at most, sorry. I thought it was at most.
Well, it's at most K if I am going to call it an at most K cover. But if I say K cover, I mean exactly K times. Every edge has to appear exactly in K members of the family.
Oh, okay.
Okay?
Okay. Okay, now I see why you need to repeat. You might have to repeat sometime.
Right. I mean, for example, just take a cycle, right? A cycle itself, if you don't allow to repeat, then it doesn't have a cycle 2 cover. So just to make things nicer, we allow repetition of the same member, and now we have this very pretty conjecture.
Okay.
Yeah? Okay, good. Any other questions or concerns? All right. So if not, let us leave aside cut edges and let us move to cut vertices. Let me start a new page. All right. So as you can guess, cut vertices is related to the notion of vertex connectivity. Okay, so it's very similar to a cut edge. Consider the following graph. And consider this vertex. Notice that this vertex, if you delete it, then your graph disconnects. Right? Such a vertex, we are going to call it a cut vertex. And to make it a more general definition, a vertex V of a graph G is a cut vertex if, as before, the number of components of G minus V is strictly greater than the number of components in G. How big can this quantity be?
Degree of the vertex.
Degree of the vertex,
Yeah.
right? Exactly. So you can't say here that you will get exactly 2 components because your graph could look like this. You could get 3 components. So unlike in the case of an edge, you can actually have arbitrarily many components upper bounded by the degree of the vertex, right? Because what would happen is each of these could be separate components. If the degree is 4, you will not get more than 4 components than the previous graph. Okay? Good. All right. So let's go back to connected graphs for a minute. A graph G is connected if and only if there exists a UV path for all pairs of distinct U and V in the vertex set of the graph. Right? That's just a definition of a connected graph. Either you can use walks or you can use paths, they turn out to be equivalent. Okay? So, can we get something similar for graphs that do not have cut vertices? Can we get a similar result for graphs without cut vertices?
I think there will exist 2 pairwise internally disjoint paths between every pair of vertices.
That's right. That's right. So we get 2 internally disjoint paths between any 2 vertices. So that is actually the next theorem, which we will prove in full detail. And it's actually a very important proof because it's one of those proofs where we have to be very careful with how we write things. Otherwise, we get into a huge mess. Okay, so that's one of the reasons I want to prove this result in full detail. A connected graph has no cut vertices if and only if you take any 2 vertices, U and V, then there exist 2 internally disjoint, I'll define this, UV paths in the graph. Okay, so what does internally disjoint UV paths mean? So you have the vertex U, you have the vertex V. You will have 2 paths which do not share any other vertices. So the vertex set of P1 intersection the vertex set of P2 is exactly the set U and V. Well, they are both UV paths, so you can't avoid that. But apart from U and V, there is no other intersection. Okay, and notice that this implies that they don't have any common edges, because if they have common edges, then they will have another common vertex. Is this a correct statement as it is written? Can somebody give me a counter example to this statement?
Which statement?
This theorem as it is written, is it a correct statement? Or are there some small counter examples?
Sir, I think K2 is a counterexample.
K2, exactly, right? There are no cut vertices in K2, but between any two vertices, there is only one path, right? So it turns out we just need to say of order 3 or more. By order, I mean the number of vertices of the graph, right? So order is the number of vertices. Okay? So we want to prove this. Another point I want to make here, notice that having two disjoint paths between vertices u and v is the same as saying that they belong to a common cycle. Okay? So this is the same as saying u and v belong to a common cycle. Of course, the reason we are defining internally disjoint paths is because we are going to use that later. Not just for two paths, but we will use it for 3, 4, and so on. It's only the 2 case which is the same as being on a cycle. Okay? Good. So, let's prove this statement.
Sir, can you scroll the page a bit up?
Yes. Yeah?
Yes, sir, it's fine. Okay.
Okay, good. So let's, I will leave the easy direction to you as a do it yourself. Okay, this is really easy. Let's prove the forward direction. Are there any questions or concerns before we proceed with this proof? Okay. So G is a connected graph with no cut vertices, and the number of vertices of G is at least 3. Okay? And our goal is to show that between any two vertices, there are at least 2 internally disjoint paths. I'll just write int disjoint to save time. Okay. So we are going to prove by induction on the distance between the two vertices u and v. This is exactly the proof as given in Bondi-Booty with minor notational or other changes. Okay. So we will prove by induction on the distance between the two vertices, and this means the length of the shortest path. Okay. So let's start with the base case. Well, there are two distinct vertices, so the distance between them is at least 1. So let's
Sir,
look at the case.
Sir, by length of a path, do you mean the number of edges?
Yeah, number of edges.
Number of edges, okay.
Yeah. Okay. So if the distance between the two vertices is exactly 1, that means that the two edges, the two vertices are joined by an edge. There exists an edge E joining U and V. Okay? I'll give you a small do-it-yourself again, which is again quite easy. Show that this graph does not have any cut edges. So that G has no cut edge. It has no cut vertex. Using this, you show that it has no cut edge. Okay? So now what do we do? Any ideas? Any ideas how to complete the proof in the base case? We want to find a cycle containing U and V. What should I do?
The equivalent characterization of not having cut edge.
Sorry?
Not having cut edge will give us that UV is indeed a part of cycle.
Right, right. So what you can do is, I mean, you can say that because E is not a cut edge, E belongs to a cycle. That's one way to finish it, right? This implies that E belongs to a cycle, right?
Yeah.
And well, if you have a cycle containing the two vertices, this is one path and this is the other path. Okay? This implies that, so we are done. Cycle. This cycle contains U and V. Okay, so this is the base case. Now let's proceed to the induction step. Notice that this is a slightly different induction proof than the ones we have done before. The ones we have done before in this course, we were trying to prove a statement about a big graph, knowing that the statement is true for all smaller graphs. Here, we have fixed the graph, the proof works for any graph, right? And we are proceeding on proving on this particular graph by induction between, on the number of, by induction on the length of the shortest path between two vertices, right? So we are not trying to get a smaller graph. We are just trying to get another U prime and V prime whose distance is going to be shorter. And we are going to use that to prove it for our U and V. Okay? So let's proceed. So let U and V be any two vertices such that the distance between U and V is exactly K. Okay? And we know that the statement is true for any two vertices that are at a shorter distance, K minus 1 or less. Okay? Good. So, how do we proceed now? We want to prove the statement for U and V. What we will do is we will take another vertex V prime, which is at lesser distance from U, K minus 1. And we will use that to prove the statement here. Okay, so we can always do that because consider a path between U and V. Consider a shortest path between U and V. And look at the vertex that is just before V and call it V prime. Notice that the distance between U and V prime is exactly K minus 1. And V prime is an edge of the graph. And there exists an edge F that joins V and V prime. So what I'm trying to say is that there exists a vertex V prime such that this is true. Okay, and V prime is not the same as U and it is not the same as V. Okay, and how do you show this? Consider
basically V prime. So basically the V prime is the vertex just before V in the shortest UV path.
right on some shortest UV path.
Yeah, on some shortest UV path, V prime is the vertex just before V.
Exactly. Exactly. Okay.
And the distance from, can the distance between E to V prime is k minus 1 because subpaths or shortest paths will be shortest paths.
That is correct. If there was a shorter path between u and v prime, then you would get a shorter path between u and v by using that last edge. Okay? Good. So, so now we can invoke the induction hypothesis for u and v prime. By the induction hypothesis, there exists two internally disjoint paths P prime and Q prime. These are U V prime paths in the graph G. Okay. So let's make a drawing. This is the vertex U, this is the vertex V prime, and this is the vertex V. And let's say your paths look like this. This is P prime and this is Q prime. Of course, this is a slightly misleading drawing. You could ask me, well, what if the vertex V belongs to one of these two paths? Okay, so let's look at that case. If V belongs to P prime or it belongs to Q prime, then can somebody complete the proof for me?
Sir, I think then basically we are done because
We are
suppose
done.
if V belongs to P prime, if V belongs to P prime, then we can take the path, subpath of P prime between U and V.
Right.
Then that is
In
one
fact,
path, and
yeah, and in fact, I will just use the fact that there is a cycle containing U and V, right?
exactly.
So we are done. Okay. So if the vertex V belongs to any of these paths, then P prime union Q prime is a cycle containing U and V, which we know is equivalent to having two internally disjoint paths between the vertices. So done. Now suppose that the vertex V does not belong to P prime and it does not belong to Q prime. Okay. Let me color P prime and Q prime using different colors. So let's say I'll make this blue and I will make this green. Okay. Our goal now is to show that between the vertices U and V, there is two internally disjoint paths. Okay. So our plan is to use P prime and Q prime to construct. I mean, this is not enough information, so we will need to do something more fancy. But the plan is still not. The plan is still this. We are going to use P prime and Q prime to construct UV paths P and Q that are internally disjoint. Okay. And I will just write down one or two steps and ask you to try it yourself, and we will complete the proof tomorrow. So there is something that we haven't used so far. We have not used the fact that the graph does not have any cut vertices. We can use it in a more explicit way. So what we'll do is we will delete the vertex V prime, and in this graph, there is a path between U and V. Okay? Since G does not have cut vertices, the graph G minus V prime is connected. This implies that there exists a path, a UV path R prime in the graph G minus V prime. Okay? And now I want you all to try it yourself. We will do it tomorrow. right? But in the meanwhile, you should try it by yourself. See if you can complete the proof using P prime, Q prime, and R prime. Okay? I don't want to discuss this right now. I want everybody to try it on their own. You have to be careful, okay? So it's very easy to make drawings which are misleading, but if you do it very carefully, then you will be able to get a correct proof. Okay? All right, so the lecture is officially over, but I'm here for another 10 minutes or so. Is there any concerns or questions?
Hello, sir.
Yeah.
So, can we not prove this using contradiction or something?
Must be possible. So give it a try. I would have to think about it to see if there are other proofs, but I'm sure there are multiple proofs of this statement in the literature.
Okay. So,
Yeah.
what I thought was like we can consider all paths from U to V,
Okay.
and we can consider all vertices such that they are in the intersection of any two paths from U to V.
Okay.
So, um, like if we remove all these vertices, like
Hmm.
like yeah, I think we can prove that the graph might get disconnected or something like that.
Okay. Yes. But then you will have to show that there is only one vertex in your set, right?
Yeah, okay.
Right. So if you delete 10 vertices, surely the graph can get disconnected, but you don't get a contradiction right away. So there might be a way to do it, but
Okay.
I haven't thought of alternative proofs of this result.
Okay.
But I'm pretty sure there are multiple proofs of this result out there. It's a
Okay.
very basic result, so there should be many proofs.
Okay. Thanks, sir.
Okay, you're welcome. Any other comments, questions? So I hope everybody has started looking at assignment 1 and started trying it as well. I want to mention that you don't need to collaborate with the same people for different assignments, but for any fixed assignment, you can collaborate with at most 2 people. And those 3 people in that case, or 2 people, would then be one group, right? But on the next assignment, you can collaborate with anybody else. So there is no dependency between the assignments in terms of who you collaborate with. I'll probably announce this again tomorrow. So I'll stop recording now.